So yes, thank you everyone for bringing me here to present on Total Control project. Also to mention as well, I'm just going to present a little bit about a similar project, Farm Corners, which has the same sort of research institutes working on the same problem as well. So which is Farm Corners. So my presentation is really just going to focus on the wind farm control aspect and how it relates to ancillary services provision as well. I'm also going to focus on the wind power plant control elements, which you would see in the presentation slides. I believe Alistair will focus on the flow control aspects as well, and we have other presentation as well, which will show like the lighter um, kind of situations we'll be running on the wind turbines as well. We'll be using in the project. So just a brief overview of the agenda. So just talk a bit about farm control, part of the recent work that's been happening as well in terms of trying to distinguish between terminologies around wind farm control, talk a bit about the turbine control, converter control, and dive into some of the work I've been doing as part of the deliverables in the project that's involved with the electrical system design and having to test that for future ancillary services provisions as well. So this slide is a slide that comes out from one of the outputs from the Farm Corners project, and this is more or less done by a number of the research institutes trying to sort of like clarify between terminologies of what exactly is wind farm control. So as you can see in the diagram, there are different elements that comes into wind farm control. There's the wind power plant control aspect, which has to do with the well-established sort of like designs already that comply to the local grid codes and grid integration. So this usually has to do with mostly the electrical aspects of the things involved in wind farm control. And also another part which has been heavily talked about is issues around the flow side of things, so wind farm flow. And this has to do with the new recent developments, wake steering and other sort of like new techniques that can be used to maximize power extraction and alleviate the loads on wind turbines as well. So wind farm control, which is a term which we've sort of like used a number of times from this sort of like summary from the work in this Farm Corners project, is seen to be sort of like an umbrella of them for both, which covers both the electrical aspects as well as the aerodynamic aspects of that as well. And as the convention as well, the turbine control has to do more focused on each turbine and how that each turbine controls the energy production, load reduction, and other general safety aspects, which needs to be adhered to comply with the different grid codes as well in different regions. Converter control goes into the more lower level of things, which has to do, things around voltage and current control, and how, with the available wind speeds, you keep to the set points which you need to adhere to for different modes like power production as well in the wind turbine. So you can see in the diagram on the right, that just shows the difference of like terminologies used as well as the timescales involved. Converter control usually spans between a few milliseconds to much lower resolutions, higher resolutions rather, and wind turbine control, going to the region between a few seconds, and aspects of wind farm control, including the power plant side and flow control side, could go from minutes to days as well. So just to start off with the turbine control aspect, as we all know, turbine control probably has to do with things that have to do with the different sort of modes of operation of the turbine in terms of how you capture the available energy from the wind, how you make sure that while it's doing the operation, the loads are kept to its limits and all safety and protection mechanisms work as expected. So this is just a conventional way which most wind turbines, as you will see, would have it: startup modes, power production modes, issues around how you could do a fast stop, a normal stop in operation as well, and also you can do like an emergency shutdown as well if there are issues to do with the turbine operation as well. And as we all know, this is based on the controller that controls different subsystems such as the pitch, the yaw angles, generator tug, and converter as well in there as well. In there really is part of the main things is to seek to how you can get the highest efficiency operation for each turbine that maximizes the power you can get out of that as well. There's also a high sort of reliance in terms of the safety operation of all the turbines as well in wind farms and under the different wind conditions as well. As we all know, PID or PI controllers are mostly used, but there are more advanced sort of like controllers, which are being looked into, sort of the model predictive controllers within the TotalControl project as well, and see how those can be sort of deployed in wind farms as well in the future. General sort of knowledge of wind turbine control, torque control, generator torque control, speed control, which has to do with controlling the aerodynamics and keeping the pitch angles and the rotations of the blades as well to where you expect them to be as well. Aspects which has to do now with converter control, going much finer down into that, has to do with the powertrain of the turbine. Usually you have the two converters there, the drivetrain converter and the grid size converter. And the primary function for this is just to realize the outcomes from which the commands from the turbine controller are saying they should do. And these are usually based on performing like a vector-based controls. We transform your ABC variables to DQ variables and through Pax transformations. And you sort of use your PI controllers to do power control tracking and current control tracking, which minimize the errors between your reference values set by your power set controllers, so power set points, as well with regards to the reverse set point values which you need to follow to keep the operation as well. So the aspect which really want to focus on with the TotalControl project is what we'll be doing on the power plant side of things, which has to do with looking at the electrical system as well. So in terms of wind power control, these are the three main things which really you need to sort of start to comply with in order to have an efficient operation of your wind farms. One is grid code requirements, so which are the technical requirements which must be complied to to connect wind farms to electrical grids. Other aspects have to do with how you generate revenue from your wind farms. So in the energy markets, you need to bid into be it the intraday, day ahead, or balancing markets as well, and sort of different revenue strategies or schemes you can use in different countries as well to basically make some revenue from the operation of wind farms. The aspect which the TotalControl project focuses more on is on the ancillary service market side of things. So at the present moment, your wind farms are not operating any of the ancillary services that has to do with like fast frequency response. And that's part of the things that we believe that wind turbines are going to be able to do in the future. And that's where the focus on the TotalControl and the farm corners projects are really looking to see how we can bridge that gap and progress wind farms into that operation as well. So you're going to be looking at the moving from the typical ways of how you develop the wind farms for maximum power generation, and bringing in the market mechanisms to see how you can switch that into like maximum revenue generation sort of like targets as well. And bringing in services such as frequency response, which are going to be operating at much shorter windows between milliseconds to minutes, also as well as provision of the sort of additional reactive power sort of requirements as well, and even new schemes such as like inertia and black start coming into place as well. So these are all new sort of strategies and which needs to be deployed on wind farms and wind turbines as well. And as you can see, by doing that, we will be moving to a more complex sort of interactions of how the wind turbine interacts with the wind farm, and this requires a bit more understanding in terms of testing, validation, and development of these advanced controllers. So within the project, working with Syntef to focus more on the electrical system side of things. That has to do from the onshore transmission to the offshore transmission connected to the wind farm, and the modeling of all the different elements such as the transformers, the cables, and the turbines in high fidelity models using a simulation software that are more electrically focused, just PSCAD. And that's what we've been doing. So we have a reference wind farm, which is described in the project, which gives all the different parameters for the transformers and cables. And we model that on the simulation as well to get a replica model of that description of that wind farm. as well as design and this new advanced wind farm controllers that have to do with the not just the electrical side of things, but also the farm flow control side of things, which dynamic wake steering and other aspects also included in that. And that combines into integrated model to realize and do some testing and validation. So on our side, on the ORI catapult, we're most focused on the electrical system design. Syntef has been working on the flow control design. And part of the project is to integrate both models together to have a combined sort of aeromechanical / electrical detailed model that will be able to do and different case studies to, as I mentioned earlier, keep to the different grid compliance requirements, and also test different ancillary services, markets, and situations as well. So that's what the project is on as well. And the link down there is just a deliverable, which is one of the early outputs from the project, which sort of describes where we've gotten to so far, especially with the wind farm controller design as well. So what happens there is that we have a more like a simplified version, which is a baseline controller that starts to add not just electrical elements in, but also the flow control elements in. And tying those two together, we're starting to bring it together to form an integrated model where we can do sort of similar tests as well to see how this would operate and see what sort of new interactions on the power system side of things, and seeing if for example, changing your sort of like alignment of your alignments and the wake steering methods might affect the power system design in any way, and trying to see how different sort of fault modes and how that might affect that as well as the requirement for maybe new sensors to be added, or how you switch back from different modes as well. So that's part of the sort of areas within that sort of work, which we're working on in TotalControl at the moment. And this slide is just an example of the model already built. So each of the wind turbines, as you can see there, has a detailed electrical powertrain model, which has the power control aspect and the current control aspect with the vector controls in there. And it basically has your power production strategy curves and can basically respond to different wind speeds and give different performance outputs as well. As well as that, you have all the different electrical elements, including the filters and the transmission cables and everything all modeled in there at the converter side. And you have a 320 megawatts model there with about 32 turbines, which are all interacting together in an electrical system design, and including the aeromechanical side of things, bringing in wind speeds as well to see. So the diagrams there are just an example of a prior production mode scenario being run. And as you can see, the wind turbine controller response as well, be responding to a set point there of 10 megawatts, which change from each of the turbines as well, and that produces the overall output as expected. So where we are at the moment is now beginning to integrate the advanced wind farm controller model into this, and starting to run the test between the two as well. So yes, just a summary of the next steps which we're working on as part of the project. As Paul mentioned, this is coming to my end at some point in next year. So we're going to be working on just two scenarios. One is basically to put in a replication of a frequency response scenario there of a fault case to see how the wind farm controller will respond, and analyze different measurements from the electrical system to see how it performs as well, and see if there are sort of any scenarios we should be looking at, sort of any incentives that could sort of curtail power generation instead of like alleviate loads as well. So the wind farm control model as well is able to switch between those two situations and give some sort of result, and we can see how that sort of shows on the power system interactions. And the second scenario there is more or less we're trying to understand if you're going to be switching from the standard way of how the wind farm controller works into a more advanced situation. Could you switch back and have a fallback strategy in case some of your sort of advanced methods and sensors fails? So we could always keep the wind farm operating even in its conventional mode if, let's say, things go wrong when it switches to an advanced mode. So we want to sort of identify different sensors that we should be monitoring and understanding what happens if there's a communication loss, and if like the optimization algorithms, for example, model predictive controls or other aspects fails, and provide some recommendations as well into the design for future wind farm controllers as well. So that feeds into an additional activity that looks into the standards for wind farm controllers, which is done by DNV in the project as well. And we'll be using this sort of simulation models to give some simulation results just to improve the understanding of what the future sort of standards for wind farm control should consider as well. So that's my aspect of the presentation. Just hand over to you, Alistair.
John, thank you very much.
Thanks, John.